Hello everyone, this is Rob with Redshift. This is the second part of our Redshift for Maya video. We'll do an overview of camera, lights, shaders, visibility flags, tessellation and displacement. First up, we'll introduce you to cameras. Redshift translates almost all of the Maya camera attributes, such as angle of view, focal length, camera scale, near-far planes, as well as most of the film back attributes, with the exception of the pre-post scales and film controls. The native Maya depth of field attributes are also supported by Redshift, but only when there is no Redshift bokeh assigned to the camera or render global lens shaders. And the orthographic option is also supported by Redshift. Now further down, we can see that Redshift added some custom attributes. The first of these attributes is the camera type, which allows you to render using fisheye, spherical, and cylindrical projections. And please note that cylindrical projections by default look the same as spherical ones, except you can change the horizontal and vertical field of view. And below that we can see that Redshift also added environment and lens shader connections. These connections allow the user to override the environment and lens shaders specified in the render globals. This type of override is useful when different cameras need different bokeh or photographic exposure settings. And if you need to add more than one lens shader, then you can use the additional lens shaders option. And up next we'll talk about lights. Redshift supports the existing native Maya light types and introduces a few Redshift specific lights as well. Physical lights are the most common lights in Redshift. We'll describe them in detail shortly. IES lights allow the usage of real, measured photometric light data. Most real-life lights do not emit light uniformly, so in order to render them realistically, we need photometric data which accurately defines the shape and intensity of these lights. Portal lights are useful when rendering interiors which are affected by outside environment lighting. A portal light placed where the windows are can help cast environment lighting into the room in an efficient manner, thereby reducing noise. And dome lights allow the usage of HDR image in your scene. This is called image-based lighting and lets you light your scene realistically and efficiently. Now let's take a look at an example. In this scene we have three dragons lit by a rectangular Redshift physical light. We'll now describe the properties of the light. The first option defines the light type. We support area lights, which have physical size and shape, point and spotlights, and infinite lights, which are useful when modeling bright distant lights like the sun or the moon. Moving on to the intensity attributes, the intensity multiplier property at the bottom is self-explanatory. It controls how bright or dark the light is. The intensity mode settings defines whether the light color will be adjusted via RGB values or via temperature values in Kelvin. The default unit type for the light intensity is image units, but you can also choose physical intensity units such as watts. So in this case, the value in the intensity multiplier property is in watts. The ray contribution settings let you fine-tune how much light affects diffuse or glossy surfaces. You can make the light affect only specular surfaces, or only diffuse surfaces, or you can scale the contribution to simply dial back the effect on a particular surface type. The decay settings allow you to control how the light intensity decays with distance. Setting it to none means the area light won't decay with distance. Depending on the decay type, you might have to adjust the light's intensity. As you can see in this example, our intensity is too large for a no decay light, so we have to reduce it. Another decay option is linear decay, where the lighting becomes gradually dimmer between the start and stop fall-off ranges. Out of these decay options, inverse square is the only one that is physically correct, which is why it is the recommended default. The area controls allow you to change the specific shape of the light. Apart from these basic shapes, you can also link a light to a mesh in order to turn the mesh into a light. This is useful when your light cannot be described with basic shapes, such as if it was a neon sign. The visible setting controls whether the area light will be visible from the camera or not. And the bidirectional setting allows planar area lights, such as rectangle and disc, shine on both sides. Now let's see what happens when we increase the size of the light by scaling it. As the light becomes larger, notice that it becomes brighter and its shadows softer. This is physically correct since the intensity is measured per unit area. If you prefer to maintain a constant intensity of the light as you change its size, you can turn on normalize intensity. Notice that the light now appears dimmer because the intensity is not affected by its size, so we now have to increase the intensity of the light by quite a bit. And now if we scale the light back down, notice how the intensity remains constant as we shrink it, but the shadows remain sharper. Area lights can produce noise when rendering, sometimes also called grain. Increasing the samples parameter will produce smoother, less grainy shadows. This parameter has only an effect during bucket rendering. Most scenes will render smoothly when this parameter is set to a value of around 200 to 500. And the spot settings only apply when the light type is set to spot. The shadow controls define whether a light casts shadows or not, and also how opaque or transparent these shadows are. And the softness control is useful for lights that are not area lights, such as point or spot or directional. Without the softness control, these light types would always be casting sharp shadows. Lights can also cast volumetric lighting. Let's enable a volumetric scattering shader to see how they look. Now you can see the volumetric lighting. The volume contribution scale controls how much volumetric lighting a light will produce. Brighter lights will naturally produce more volumetric lighting, but sometimes that might not be desirable. In such cases, you can use the contribution scale to tweak the light's volumetric effect. The volume num samples can help when rendering in bucket mode. Increasing the samples will remove grain from the volumetric lighting. And below that we can see the photon settings, but those will be covered later in a different tutorial. Now let's look at our IES light, which is currently disabled. As you can see, our IES light has a more complex shape than our Redshift physical light. That shape comes from an IES profile which we assigned previously. IES lights share quite a few properties with the physical light, such as the ray contribution scales, shadow and volume controls. IES lights are typically used for architectural renderings, where real lights are required to accurately show how rooms are going to be lit. And up next we're going to talk about projector effects. One neat trick you can do with Redshift lights is assign shaders to their color input. Amongst other things, this can be useful for achieving projection-style lighting effects. In real life, texturing a light happens via special light filters, which are sometimes called gobos. Here we have a simple scene containing 3 lights, a quad light, a spotlight, and a point light. A gobo texture is assigned to all 3 lights. And before we proceed, one thing to keep in mind is that you should set the gobo texture's default color to black instead of grey. This is because, due to filtering, Redshift lights might attempt to read outside the valid range of texture, and we typically want that invalid range to be black, which means no light. Not doing so means that grey lighting might leak into the colour of our textured lights. And for the same reason, the wrapping option should also be disabled, so the projection doesn't leak neighbouring colours when sampling the edges of the gobo textures. So, now let's take a look at how the gobo texture behaves when combined with all of these basic light types. As we can see here, when a gobo texture is assigned to an area light, the visible geometry of the light also contains the texture. As far as lighting is concerned, we notice that the emitted light doesn't appear to project the gobo texture onto our geometry though. Instead, we seem to be getting some kind of blurry version of it. This is physically correct. Area lights are not emitting light towards a focused range, but instead emit light in all directions. So, as a result, we get this kind of blurred light emission. Now let's see how our spotlight behaves with the gobo texture. Now here we can clearly see the gobo texture projection on our scene geometry as expected. This is because spotlights are focusing their beams in a way that's similar to how a cinema projector works. Please note that spotlights can still produce blurry shadows via the shadow softness options. So notice how the shadow of the sphere is sharp by default, but when we increase the softness parameter, the shadow becomes blurrier but the gobo does not. But for your convenience, Redshift includes a softness effects gobo switch, which allows you to choose whether the softness should affect the gobos as well. Okay, now let's see how the point light behaves. As we can see, the result is similar to what we got on our spotlight, except for the fact that the image is projected all around the light and not towards a particular direction. And next up, we're going to look at dome lights. Here is a scene lit by a single dome light. As mentioned previously, the dome light allows you to light your scene using an HDR texture. This can produce realistic and complex lighting easily. And depending on the format of your HDR dome texture, you'll need to choose the appropriate map type. The most common type on the web is spherical, which is also known as latitude-longitude. The dome light has exposure controls which allow you to make it brighter or darker. Exposure is measured in powers of 2, so 0 translates into intensity of 1. An exposure of 1 means twice as bright, 2 times 4 times as bright, and so on. Negative numbers will darken the dome light. -1 will make it half as bright, -2 will make it a quarter as bright, and so on. The hue, saturation, and tint of the dome light can be adjusted to fine-tune the dome light's color. And looking quickly at some of the other options. The flip horizontal can be useful as some 3D apps have a different convention for the x-axis of the dome light. sRGB and gamma can be useful depending on the contents of your image. In most cases though, they should be left at the defaults. The scales, shadow, volume settings work the same as with your Redshift physical lights as discussed previously. And the environment enable option below controls the environment visibility. And finally, regarding the backplate options, sometimes HDR images come in pairs, a dome image for lighting everything, and a separate background image to be used as the backplate. And finally, if you want to rotate the dome image light, you can do so by rotating its gizmo in the viewport. And next up, we'll talk about shaders. On Hypershade, you can type Redshift to filter out the Redshift shaders. We can see the various shaders that Redshift has added to the Maya's list of shaders. Redshift supports some of the existing Maya shaders too, such as Phong, Lambert, and Ramp for example. But probably the most common shader is the Redshift architectural shader, so we'll cover that one here. So if we take a look at the Dragon material, let's look at the Redshift architectural shader options. As you can see, there are a lot of options, so let's collapse everything first so it is easier to read. So, the RS architectural shader has a diffuse layer, 2 reflection layers, a primary and secondary one, and it can do refraction and ambient occlusion. If we open the diffuse layer, we can see the color and roughness controls, which are self-explanatory, and weight. The weight controls how much diffuse we want our shader to have. One thing to keep in mind with RS architectural shaders is that it is layered and energy preserving. The way layers are stacked on top of each other means that even if I make the diffuse weight 1, this doesn't mean that my surface will be perfectly diffuse. This is because the weight of each layer takes away from the previous one. If we look at the reflection layer, we see that it has a weight too, which we'll discuss shortly, and this will take away from the diffuse layer. So if we close the diffuse layer, let's take a look at the reflection layers. The glossiness controls how rough or shiny the reflection will be. Higher values mean higher glossiness, and therefore a more shiny look. In bucket rendering mode, adjusting the samples is important to get rid of any grain caused by low gloss reflections. Here we are rendering an IPR, so the samples parameters don't matter. The Fresnel controls the strength of reflections around the edges of the object versus the inside of the object. This can be achieved either via the index of refraction, which can be found in the refraction controls, or via the facing, perpendicular, reflectivity and curve fall-off properties. For physically correct results, we recommend using the index of refraction method. If the material is a conductor, its K value is also required. Examples of conductors include most metals. Examples of dielectrics include wood, plastic, glass and water. There exist tables on the internet that explain the various different refraction indices and K values for most real-world materials. But if instead of physical correctness, tight control of reflection is required, we recommend using the facing perpendicular reflectivity controls. These allow the user to specify the amount of reflectivity on the silhouette versus the inner parts of the object, and also how quick the gradation of that reflectivity should be. So we'll quickly disable diffuse and secondary reflection to show the effect of the facing perpendicular reflectivity and curve fall-off controls. Okay, as we can see, we have a strong facing reflectivity and weak perpendicular reflectivity. When this is the case, adjusting the curve fall-off to values less than 1 will exaggerate the fall-off effect. And here we demonstrate how to get reflection only on the edges of the object by setting the facing reflectivity to 0 and perpendicular to 1. Adjusting the curve fall-off allows the effect to be tightened around the silhouette. Instead of using the facing perpendicular controls, one can use the index of refraction option. Doing so will use the IOR value of the refraction settings to produce a physically correct Fresnel result. Okay, let's restore all our default reflection properties. And let's re-enable the second reflection layer. A second reflection layer can be useful in a variety of scenarios. For example, we can invert the facing perpendicular Fresnel controls between the two reflection layers, allowing us completely different reflection layers for the inside and the rim of the object as shown here. And if we change the color of the second reflection layer, you can see how the effect is exaggerated. Now moving on to the common reflection attributes. These attributes are applied to both reflection layers. The first option is metal material, which basically tints the reflection colors with the diffuse color to emulate one of the color properties of metal materials. And next we have highlight versus reflection balance, which is used to tune the amount of specular light reflections versus reflections of objects in the scene. By setting this value to 0, only reflections of the objects such as the ground and the other dragons are visible. And now I'm going to show you a quick demonstration of the anisotropy controls. Here is a simple scene that shows the effect more clearly. The anisotropy controls essentially allow you to adjust the shape of the material roughness. This can be used for effects such as brushed metal, which gets its unique look due to imperfections at a microfacet level. Adjusting the amount between 0 and 1 allows you to tune the roughness along one axis, while values between 0 and -1 tune the roughness along the other axis. You can further control the direction of the effect by using the rotation control. And the surface orientation gives you further control of the direction by specifying a UV map tangent space. And finally, you can achieve some interesting effects by driving the amount and rotation properties by textures. For example, you can get a brushed metal effect by texturing the amount. Here is a simple scene we made earlier that applies a texture to the rotation to get a beaten metal effect. Now it is important to note that there should be no texture filtering enabled for this kind of texture, otherwise you will get incorrect results when there is a jump in rotation values. If we go to the File node, you will see some Redshift attributes. The Enable Filter option here should be set to None. Okay, and now we're going to talk about refraction. This scene is configured to be using reflection and refraction. The refraction weight dims or brightens the refractions. Reflection is using dielectric Fresnel setting, which is automatically linked to the refraction IOR. Setting the IOR to 1 makes the rays go straight through without being bent at all. Also notice how reflections have disappeared. As discussed previously, the IOR affects the Fresnel reflection strength, which is 0 when the IOR is 1. And with higher IOR values, the rays will get more bent and the reflections will get stronger. Lowering the glossiness can produce a frosted glass effect. But remember that the IOR has to be pretty high for this to work. If the IOR is set to 1, then no matter how low your glossiness is, you won't get the frosted glass effect. And just like reflections, any glossiness can produce noise, so the number of samples has to be set sufficiently high to combat this when rendering in bucket mode. Okay, we'll go through some other settings here. Firstly, the Disable Refraction Bump Mapping option allows you to turn off any bump or normal mapping effect for refractions, but we'll talk more about bump mapping shortly. And the Disable Ray Bending option is useful for emulating very thin glass surfaces without you having to model actual thickness. When enabled, there will be no ray bending as if the IOR was set to 1, but the Fresnel effect will still behave as expected. The Enable Refractive Caustics option will make transparent shadows solid, which can be useful for glass objects that expect their shadows to be defined by photon caustics instead. Not enabling this option on caustic glass objects can result in the sometimes unwanted effect of double lighting that comes from both the transparent shadow and the caustics. And finally, the Allow Global Volume Scattering option allows global light volume scattering of fog to happen inside a closed transparent object. Now in real life, closed mediums, such as a sphere for example, would not be affected by atmospheric effects in the air. So, if you have a closed object and you want a more realistic interaction with global fog and scattering, you should disable this option. Okay, now let's enable the fogging here. Using this setting, as rays travel through this object, they will become dimmer the more they travel. This is emulating transmission through a medium and is great for producing convincing looking tinted glass. The higher the distance setting, the less light is absorbed by the material. The fog end color enables tinting those rays as they pass through the object. And disabling this means rays get dimmer as they pass through without tinting. Before we talk a little bit about the built-in ambient occlusion feature of this shader, let's go back to the diffuse properties and take a look at a neat option useful for lighting thin, translucent objects such as paper and leaves. Translucency is a cheap alternative to proper subsurface scattering and is used to achieve backlighting or scattering on very thin objects such as paper or leaves. It should be noted that real subsurface scattering requires object thickness to function anyway, so in cases where there is no object thickness, translucency is the only viable alternative to get a backscattering effect. Here we have a simple scene to demonstrate the effect of translucency. Inside the dragon object we've placed 3 lights. When translucency is not enabled, the surface is effectively solid and the light cannot penetrate through. But when we enable translucency, you can now clearly see the effect of the lights inside the object. The translucency settings are similar to the diffuse settings above and describe the diffuse colour of the surface when backlit. There is a weight control to scale the amount of backlighting, and there is a colour control that allows you to choose a different diffuse tint for the backlighting. This colour is typically the same as the diffuse colour, but you can use any colour or text you like for more interesting effects. So, for example, when rendering a leaf, you could apply a different diffuse texture for the translucency colour that also contains some of the natural subsurface scattering effect. And last but not least, we'll touch on the built-in ambient occlusion or AO feature of this shader. AO is essentially a legacy feature that was primarily used to get cheap but fake GI when real GI was impractical. Nowadays, GI is practical, so AO is not as useful, but some people still like to use it for artistic purposes or for dirt map effects. AO is most noticeable where there are creases and corners. So first, let us disable the dome light in the scene and enable a non-shadow casting light to better demonstrate the effect. So without global illumination enabled, as you can see, the contact points between the ground and the dragon contain no shadow and look flat and unrealistic. So let's now enable AO on both materials. Now with AO we have nice soft ambient shadows around the contact points, giving the objects more presence in the scene. So looking at the options, the first thing we see is the combine mode. This tells us whether to add the results of the AO for a fake ambient lighting effect, or to multiply the results for accentuating occlusion around creases and corners. Here we are using the multiply mode. Below that, increasing the samples value will help reduce noise during bucket rendering mode. And the max distance option controls how far the AO rays are shot, with 0 meaning the length of the scene. You can use this option to better localize the effect, resulting in less overall occlusion. If we take a look at the dragon material, you can see that our max distance setting is relatively short. This is because we want to try to limit the occlusion to around the contact points with the ground and don't want the dragon to overly occlude itself. So if we set the distance to 0, you can clearly see that the dragon gets darker because of this. The spread option allows you to control how the rays are distributed, with 0 being the widest distribution over the entire hemisphere. Values less than 1 will gradually produce more exaggerated results. The fall-off option allows you to control the tightness of the transition between occluded and unoccluded results, with values greater than 1 biasing towards occlusion and vice versa. And the invert normal option flips the surface normal so the occlusion rays are shot in the opposite direction. And the shadow and ambient colours describe the tints for the occluded and unoccluded results respectively. Finally, it should be noted that we also have a standalone ambient occlusion shader node with similar options to the built-in one here. The standalone node is useful for such effects as dirt mapping, where it can be used to drive the blend weight between two blended materials. For more detail on the features of this node, please see our online documentation. And up next we'll talk about bump and normal mapping. Bump and normal mapping is a great cheap trick to get extra surface lighting detail through perturbing normals instead of perturbing geometry. Let's take a look at an example of bump mapping. So inspecting the dragon material, we can see there's a Redshift bump map node connected to the bump port of the material and a texture file connected to the Redshift bump map node. The texture is of a scaly looking noise that will stand out for this demonstration. So let's enable the bump map node. And now we can see bump mapping. The height scale controls how strong the bump mapping effect is and is in world units. It works best when the bump scale takes into consideration the size of the object we're applying the effect to. For example, here the dragon is around 16 units from tail to head, so we need to scale down the bump significantly to prevent the shading effect from breaking down. It should be noted that the same rule applies when applying displacement mapping too. And if your bump map texture is in some weird intensity range, you can use the change range controls to adjust it. Redshift materials can also fake clear coat reflection layers. Let's take a look at our clear coat material and apply it to the dragon. As you can see, the bump map affects both the diffuse and reflection layer. To get a clear coat effect, we simply disable the bump on the reflection layer. Now we can see that the reflection layer appears smooth compared to the diffuse layer. And if you're feeling adventurous, you can try mixing multiple bump maps together using the Redshift bump blender as shown here. This can be useful for more complex looking surfaces with bump details at different frequencies. Here we have a base bump of cloth which has a distinctive pattern to it. Now we're going to blend this bump map with the scaly bump we saw in our other example. And also, don't forget to enable normalization to get predictable results when blending bump and normal maps. And finally, Redshift does normal mapping in a very similar fashion. Instead of the bump node, use the normal map node instead. And just like you can blend bump maps, you can also blend normal maps. So, We've talked about the architectural shader and bump mapping, and this is just the tip of the iceberg. Redshift supports several utility and math shading nodes which allow the creation of more advanced shader effects. For example, we support sampler info, as well as plus minus average, multiply divide, reverse, set range, and contrast. Redshift also supports several noise and procedural texturing nodes, such as solid fractal, cloth, snow, and checker, with support for more coming soon. It has its own multi-layered car paint shader with metallic flakes, and it supports efficient material blending. It has a physically based hair shader, and for a comprehensive list of supported nodes, please see our online documentation. Redshift also supports multiple UVs, as well as UDIM and UV tile textures using the UDIM and UV tile tags for efficient texture tiling. When Redshift is installed, it adds a parameter group on each shape in the scene. Amongst other things, there is a visibility section which controls if this object should be visible from camera, reflections, refractions, lights, and so on. And even though Redshift translates the equivalent Maya render stats, the Redshift options are more elaborate, so we recommend using these instead of the Maya ones. But please remember that when the Redshift visibility options are enabled, they will override the Maya render stats. These visibility options can be useful in terms of both artistic control as well as optimizations. For example, there is a switch that can make objects invisible to GI rays and another that disables GI computations. These options could be used on high transparency objects such as glass. Glass objects don't strongly affect other GI lit objects, so the visible to non-photon GI option could be disabled. Furthermore, GI effects on glass are not visually important, so the receives GI option could also be disabled. Doing so means that Redshift can skip certain visually unimportant but time-consuming computations and shorten the render times. Another important option is the Force Brute Force GI. Redshift supports certain point-based global illumination techniques such as irradiance caching. While irradiance caching can be efficient on flat surfaces, it is less efficient on geometrically complex objects such as grass, foliage, and hair. Such objects might actually render faster using brute force GI, so if your scene is using irradiance caching, the Force Brute Force GI option allows the user to override it with the brute force GI technique on specific objects. Another important option is the Casts Caustics Photons. Please note that this option is disabled by default. If you render with caustic photon emitting lights, please remember to enable this visibility option on the objects you want to produce caustics. So now we'll demonstrate the function of a few different visibility options. First, we'll disable the primary rays visible option. This makes the dragon invisible to camera rays. Secondary ray visibility refers to reflections and refractions. Notice that even though we've disabled secondary ray visibility, there still appears to be a reflection on the ground. However, this is actually a glossy shadow coming from the scene's Domelight. So, to get rid of apparent reflection, we also need to disable the Cast Shadows visibility option. And for more information about the visibility options, please refer to our online documentation. And next up we'll talk about tessellation. Apart from the visibility options, the per-shape Redshift options also contain settings for tessellation. And while Redshift is capable of using Maya's native smooth mesh settings, the Redshift tessellation parameters contain more options, such as adaptive tessellation. When Redshift tessellation is enabled, some of the smooth mesh settings will no longer function, most importantly the subdivision levels, and other options like whether to smooth UVs or not are still in effect. So here we will then enable the smooth mesh on the cube. We're using 2 levels of subdivision, so the cube has now turned into a low tessellation sphere-like object. And now we'll enable the Redshift tessellation. As it can be seen, Redshift tessellation takes precedence over smooth mesh tessellation. The default Redshift tessellation settings perform 6 levels of screen space adaptive subdivision, which is why the mesh looks smoother compared to our 2 levels of smooth mesh subdivision. Redshift supports 2 kinds of adaptive subdivision, screen space and world space. By default, screen space subdivision is enabled, When screen space subdivision is disabled, world space subdivision is implied. Screen space adaptive subdivision means that polygons which are small on screen will be subdivided less than larger polygons. Therefore, objects that are small or far away from the camera will use fewer polygons during subdivision. This is the most memory efficient option. World space adaptive subdivision means that polygons will be subdivided based on how large they are in the scene and not depending on their relative position to the camera. The minimum edge length controls how aggressive the subdivision will be. Smaller values will force more subdivision than vice versa, and depending on whether screen space subdivision is enabled or not, the minimum edge length setting will be either in pixels or world units. When performing screen space subdivision, this setting will typically range between 1 and 8, and when performing world space subdivision, this setting should be set according to the size of your scene. So here we're increasing the minimum edge length to 32. As it can be seen, the object looks more polygonal because less subdivision happened on it. Now let's restore this back to 4. And setting the maximum subdivisions controls how many times the object will be subdivided. This works similarly to the equivalent smooth mesh setting. And here we're reducing the maximum subdivisions to 2. As it can be seen, the object has not been subdivided enough, so it looks low poly. Now let's restore it back to 6. It is very important to understand what 6 subdivisions mean from a polygon count standpoint. Each subdivision level can potentially increase the polygon count by a factor of 4. So 2 levels of subdivision can increase the poly count by 16, 3 levels increase it by 64, and so on. Therefore, the poly count increase is exponential. A subdivision level of 6 can increase the poly count by a factor of 4096. So this means that if your mesh originally contained only 1,000 polygons, it could now contain 4 million polygons. Adaptive subdivision tries to prevent this maximum number of subdivisions from being reached. With screen space subdivision, the polygons will stop tessellating when they are small enough in screen space. And with world space subdivision, they will stop tessellating when they are small enough in world space. However, if the screen resolution is very large, the polygons will need to be subdivided more to reach the minimum edge length. Similarly, if using world space tessellation, a huge object might need more levels of subdivision. It is therefore important to be able to recognize those problematic cases and be ready to adjust your subdivision settings accordingly, otherwise the rendering performance could suffer due to the sheer number of polygons generated during subdivision. And even though Redshift doesn't have an explicit fixed subdivision setting, you can do that by disabling the screen space adaptive and setting your minimum edge length to 0. This will ensure that your maximum subdivisions will be reached. And we'll talk about the smooth subdivision option a little later. The final tessellation option is the out of frustum tessellation factor. This controls how much subdivision should appear on objects that are outside the camera's field of view. This helps performance by subdividing these objects less. The larger the factor, the less subdivision will happen for these objects. Setting this setting to too high a value, though, can create visual artifacts and reflections and shadows cast by objects outside the field of view. In other words, it will make it obvious that these objects are subdivided less. Now, one great feature of Redshift tessellation is that it also supports edge and vertex creases. So here's a quick test. We go to the Edit Mesh, Crease tool, and we select an edge and crease it. Okay, and now we can select a vertex and crease it. And up next we'll talk about displacement. Redshift can perform displacement mapping. Here we have a scene similar to the one used on our tessellation tutorial. The difference here is that a Redshift displacement shader is connected to the shading group of the cube. So let's take a look at that in Hypershade. And also in the attribute editor. In the hypershade we can see the shader connections. A file node is connected to a Redshift displacement node, which is in turn connected to the appropriate Redshift port of the shading group. And we can also see this connection in the attribute editor. So looking at the options of the Redshift displacement node, we can see that Redshift supports both height and vector displacement maps. Furthermore, it is possible to do range remapping of the original displacement in case the texture is in some arbitrary numerical space. This is similar to the bump node options we explored earlier. And the enable bump mapping option helps enhance high frequency displacement detail without requiring extremely high tessellation levels. It does that by adding an automatic bump map during rendering. Also, in case you can't find this option, prior to version 1.2.31, this was incorrectly named Enable Auto Bump. So, even though this is the most basic displacement shader graph possible, Redshift allows many displacement possibilities. For example, you can blend multiple displacement maps together, as well as using procedural nodes for displacement purposes. Okay, after configuring our Redshift displacement shader graph, we also have to enable tessellation and displacement on the object as shown here. And if we render this, we can see that the cube contains a brick-like texture detail. Notice the silhouette detail as well as the micro shadows on the surface of the object. One tessellation option we didn't mention previously was the smooth subdivision one. Smooth subdivision can turn an angular object like a cube into a round object like a sphere, and conversely, disabling smooth subdivision helps preserve the angular shape. Also notice that, for this example, we reduced the minimum edge length to 2 to get better definition in our displacement. This means that more tessellation had to happen. Displaced meshes can often require more aggressive tessellation settings in order for the micro shadows and silhouette detail to be well defined. We also increased the max subdivisions to 10 from the default 6 because the cube by default has very low tessellation. Now, looking at the object's displacement options, we can see maximum displacement and displacement scale. Maximum displacement is a hint to Redshift about how much displacement the shader will apply to the object. If you're using height-based or grayscale displacement, this second setting can often be left at 1. If on the other hand you're using vector displacement or have elaborate displacement shader graphs that might be adding or scaling the displacement textures, this setting might have to be increased according to your scales. Not doing so means that displacement might be clamped and will not render correctly. On the other hand, setting it to high values means the rendering performance might suffer too. Here we demonstrate the kind of visual artifact you can expect if the maximum displacement setting is too low. As it can be seen, the geometric detail was clamped and the object now has become flat. The silhouettes and any micro shadows have been clamped to the point where they are now almost invisible. However, because our displacement shader had bump mapping enabled, the auto bump effect still gives the impression of some surface detail. So let's put it back to 1. And the displacement scale controls how strong the displacement effect is. While you could change that via the displacement shaders, having such an option on the objects themselves can be convenient for quick tweaks. Here we see how the displacement scale changes the look of the object. This concludes the second part of our Redshift for Maya video. For more information, please visit the documentation and forums sections at www.redshift3d.com. If there's a particular topic that you'd like to see covered in future videos, please let us know in our forums. Cheers.